So I would like to talk about Gromov-Hausdorff distance width boundary today. So here's an outline of this talk, and I would like to take a review on Gromov-Hausdorff distance first, and then I'm going to give questions and motivations. And then I'm going to define Gromov-Hausdorff distance width boundary, which is a variant of Gromov-Hausdorff distance, but for non-complete metric spaces. And in order to give a compactness theorem, I would like to introduce these two boundary controls, AC property and uniformity. And I'm going to state the compactness theorem later. And I'm going to present some other results as well. And this talk is based on the preprint already available in the archive and the second one that I'm work in progress. So I would like to start with the definition of Hausdorff metric. So we fix a metric space first and then take two sets A and B. And the Hausdorff metric is defined by the infimum of epsilon such that epsilon neighborhood of A contains B and B epsilon neighborhood of B contains A. And this notation A sub epsilon and B sub epsilon are epsilon neighborhood of A and B. And if the fixed space X is compact, then if you take the set of all compact subsets of X, and if you consider the Hausdorff metric on it, then it's also compact. And this will parallel quite often. So I'd like you to keep in mind. And the Gromov-Hausdorff distance denoted by d sub GH is a metric on the set of all compact metric spaces. So if we take two metric spaces X and Y, then Gromov-Hausdorff distance is defined by the infimum of Hausdorff distance between two copies, copies of X and Y. And the infimum is taken over all triples Z and V and psi. So roughly speaking, what this metric measures is that if you take two compact metric spaces and then you try to make these two spaces as close as I can, then that actually defines a metric here. So since d sub GH, Gromov-Hausdorff distance is a metric, so that means if Gromov-Hausdorff distance between two spaces is equal to 0, if and only if X is isometric to Y. But if you try to deal with non-complete metric spaces, then you cannot actually say that this Gromov-Hausdorff distance is equal to 0. You cannot say this implies X is isometric to Y. So easy example is that if you consider open disk and punctured disk, then because homology is different, so you cannot actually induce a homomorphism between these two. And there's a fact that the set of all, if you exclude non-complete metric spaces, and if you only consider the set of all compact metric spaces, then that with the Gromov-Hausdorff distance is a complete metric space. And this is due to Edwards and Gromov. Okay, so here are some motivation questions. So the Hausdorff distance is defined on the set of all bounded closed sets in a fixed metric space, and the Gromov-Hausdorff distance is defined on the class of all compact metric spaces. And pointed Gromov-Hausdorff distance, this is the generalization of a Gromov-Hausdorff distance dealing with the unbounded case. So the question one is, can one induce a metric for a class of non-complete metric spaces? In question two, if we can define a metric on a class of non-complete metric spaces, then what class of non-complete metric spaces will be complete with respect to that metric? And those two questions will be answered in this talk. So boundary version, this is what I call Gromov-Hausdorff distance width boundary. It's defined by the following. So we're going to take, we take two non-complete pre-compact metric spaces, X and Y, and metric boundary is defined by partial X and partial Y. And the Gromov-Hausdorff distance width boundary between X and Y is defined by the infimum of Hausdorff distance between two copies of spaces and the Hausdorff distance between the copies of boundaries. And we're going to take the infimum over all z and phi and psi. And anyone can define this metric, but the question is this d sub g hb a metric? And so in order to check that d sub g hb a metric, we have to prove that d sub g hb of xy is equal to 0 if and only if x is isometric to y. And it turned out that this is not true in general. And here's example 1. So if we take x to be our rational numbers in the interval 0 to 1, and y to be rational numbers in the interval 0 to 1, then of course this is x is dense in 0 to 1 and y is also dense in 0 to 1. So we can easily see that the Hausdorff distance between these two spaces is equal to 0. And if you take the metric boundary of x, then it will be rational numbers, and the metric boundary of y is our rational numbers. So Hausdorff distance between those boundaries is also equal to 0. So, but you can easily see that there's no bijective map between these two because the cardinalities are different. So this is not, d sub GHB is not a metric in general. And another example here is that, so instead of taking this definition, we might wonder, whether or not this actually induces a metric on the class of non-complete metric spaces as well. And if you consider x to be a rectangle, with the boundary, which is a straight line here, and y to be this rectangle with the boundary here, then you can see that the Hausdorff distance between these two spaces is equal to 0, and the Gromov-Hausdorff distance between these two boundaries, partial x and partial y, is also equal to 0. But there's no isometry between these two because when we look at connected components, then they're different. So this cannot induce a metric, and also this inequality holds, but the converse is not true. So in order to find a proper class of non-complete metric spaces, I would like to define M, which is the collection of all non-complete pre-compact and locally compact metric spaces. And here, the equivalence relation is defined by the existence of isometry. And the reason why I want to assume that the spaces are locally compact is because of the example 1 here. So, these two spaces are not locally compact. So that's why we were not able to get the equivalence that we wanted to prove. And thanks to local compactness of spaces, we can actually derive the following lemma, which we wanted to prove. And if we take x and y from M, then there exists isometry between x and y if and only if the Gromov-Hausdorff distance between with boundary between x and y is equal to 0. And the key to prove this one is that, of course, we decided to rule out this kind of example. So the key is the distance between x and partial x is always positive for every x inside the space. And I'm going to move on to GHB convergence, Gromov-Hausdorff convergence with boundary. We say that, so if we are given, let's say we're given a sequence of metric spaces xn and x, we say xn converges to x with respect to Gromov-Hausdorff distance with boundary if the Gromov-Hausdorff distance between xn and x goes to 0 as n goes to infinity. And there's a characterization of this convergence. So if we just have this property, then it's kind of hard to deal with the convergence sequence. So in many cases, it's very convenient to have this proposition, which says that If you have a convergence sequence, then you can embed all of these spaces into a common metric space, and then Hausdorff convergence with boundary occurs. So this is not really trivial because of the fact that we can actually embed all of these, into one common metric space at the same time, simultaneously. And I'm going to give some examples related to GHB convergence. So if we take a ball of radius R sub n, where R sub n goes to 0, this is a ball in a Euclidean space or plane, then the limit should be a point. You can imagine that. And one point is not a non-complete metric space. So in order to find the proper class of non-complete metric spaces, which is complete with respect to Gromov-Hausdorff distance with boundary, we probably need some kind of like a diameter control. And example 4 is the following. So we're going to consider xn to be this shape. And as n goes to infinity, we're going to get this part thinner and thinner. And as a limit, we can see the shape, we can see the object something like this. Then this line part is realized as a part of the limit of the boundaries. And also this is also the limit, part of the limit of the spaces. So this is kind of like a problematic part, because if you take a limit as this square, then you can only realize the boundary here. But if you take a limit space as this rectangle with this line part, then you cannot realize the limit of the boundary in that case. So we somehow, and there are two strategies, and one is give up on the boundary convergence, which was already done by Perales and Solmarny by considering like a Grood limit spaces. And the second one is, this is what I did, impose a boundary control. So in order to rule out this kind of example, I want to focus on the spaces with some kind of like a boundary control. And there are two boundary controls that I would like to work on. And the AC property is the first one. So we fix a metric space and we are given epsilon and r. And we say that X satisfies a epsilon r property if we take a boundary point, then the ball of radius R intersected with X contains a ball of radius epsilon r for some y inside X. So this means that, so even if we consider a ball in X bar, but it doesn't touch the boundary and it is contained in the ball of radius R centered at X intersected with the big X. So cusp-like boundary does not satisfy this condition. And another one is uniformity. So a non-complete locally compact metric space omega D is called a uniform if every pair of points can be connected by a curve satisfying these two conditions. And the first condition says that curve is not too long relative to the distance between 2 points. And the second condition says that if you divide this inequality, I mean both sides by A, then we'll get R sub T divided by A is less than or equal to this quantity distance between gamma of T and the boundary. So roughly speaking, this condition said that we can take a curve whose length is not too long and the ball of radius R sub T divided by A centered at gamma of T does not touch the boundary. Okay. And here's a compaction theorem with respect to the Gromov-Hausdorff convergence with boundary. So we're going to consider a sequence of non-complete locally compact, pre-compact locally compact metric spaces. And we're going to assume that X and completion of xn's are doubling with a uniform constant. And for the second condition, we impose a epsilon R property with a uniform epsilon and R. Then we can extract the subsequence which converges to some limit space X with respect to Gromov-Hausdorff distance with boundary. And the first condition, we need this because we need to have a limit, Gromov-Hausdorff limit. So we need to assume that these spaces X and R doubling with a uniform constant. And in order to have the Gromov-Hausdorff distance with boundary convergence, we need to impose the boundary condition as well. Okay, and I'm going to focus on the class of uniform spaces from now on, and I would like to set U of AR to be the collection of all bounded A uniform spaces with the diameter bound from below. So we need this diameter control because of the example that I showed already. So if you consider a ball, shrinking ball converging to one point, then the limit space cannot be a non-complete metric space. So in order to have the class of metric spaces which is complete with respect to Gromov-Hausdorff distance with boundary, we need to have, I want to consider this boundary diameter control. And here's a theorem. So M, this is the collection of non-complete locally compact precompact metric spaces with the Gromov-Hausdorff distance with boundary. This is non-complete metric space, but if you restrict your attention to the class of, restrict our attention to U of AR with the Gromov-Hausdorff distance with boundary, then this will be a complete metric space. The proof here, this is a very rough sketch of the proof, but if we take a Cauchy sequence, X and Dn with respect to Gromov-Hausdorff distance with boundary, then we can use the compactness theorem. So we can have a limit, and the limit is also a uniform space. We can prove this by Alcela-Ascoli type argument. And we still have like 3 minutes, so I would like to talk about measure Gromov-Hausdorff convergence with boundary as well. So we're going to consider measure Gromov-Hausdorff distance by these two properties. So first condition says that the isometric copies of X and so we're going to embed all of these spaces into a common metric space, and then we're going to take the Hausdorff distance with boundary. And first condition says that that goes to 0 as n goes to infinity. And the second condition is a weak convergence of measures. And in case of measured Gromov-Hausdorff convergence, we don't have this boundary term. And PI space, I'm gonna skip this part, sorry, because of the time limitation.
If you like to take some more time, there is more time, up to you.
Oh, okay. Then I would like to briefly talk about PI spaces. So metric measure spaces, given metric measure space is called PI space if the following two conditions are satisfied. And the measure, and first condition says the measure is doubling. In other words, the measure of the ball of radius 2r is controlled by the measure of the ball of radius r. The peak-Poincare inequality holds. Well, this means that the first order calculus is valid in a sense about the gradients. So roughly speaking, PI space is just a finite. This is the metric measure space with a finite dimensionality and analytically nice in some sense. And here's the corollary that I obtained combining these two results by Shiger, Keith, and Bjorn Shamgalingham. And the theorem by Chigger and Keith states that the PI space is stable with respect to Gromov-Hausdorff, measured Gromov-Hausdorff convergence. So if we have a sequence of metric measured spaces convergent to XD mu, then XD mu is also PI space. And Bjorn and Shamgalingam proved that if X is a PI space, and if you consider a domain inside X, which is a uniform domain, then omega is also a PI space. So here's a corollary. So if we have a sequence of metric measured spaces that are uniform and also PI spaces, and if we assume that X and D and mu and measured Gromov-Hausdorff converges to XD mu with boundary, then we can prove that we have that XD mu is also a PI space, a uniform PI space. And this is, the proof is very simple. So we know that the limit space is a uniform space, and in the completion X bar, X is a uniform domain. So we can apply this fact, and also by the Chigger-Keith result, we can prove that XD mu is a PPI space. And that's all I have. Thank you.